Welcome to the video tutorial series on the ADS Workbench. Right now we are going to go through configuring a 3D single row simulation. The process for generating a 3D single row simulation is threefold. One, you must define the arrow geometry definitions, and this includes the airfoil geometry, the initial flow field conditions that you want to set, the aerodynamic settings at the inlet and exit, and the end wall and computational boundaries that you want to simulate. Once you have defined the aerogeometry data, you will need to specify mesh settings, and following that will be the flow solver settings. In order to start the process, you must make sure that a geometry text file for each airfoil section exists. We will go through that in the next section. What we have here is the sample case that is included with the ADS Workbench. It is a 1.5 stage turbine that we are trying to define, and this is the first half stage vane for that turbine. The 3D geometry is defined by 5 sections, each requiring 128 points, and each defined by the same format, which in our case is x1, y1, y2. There are many formats that are available to the user, but it should be noted that the same format must be used for each section. Let's get started. First, inside the workbench, we're going to open a new 3D single row steady case wizard. Let's specify the case name as row 1 of our turbine, which we'll call that our project. Once we're done with that, we are going to start with our airfoil geometry definition. The first thing to notice is that the name of the case is also the name for your AGF file, the row 1. All of the airfoil geometry and aerodynamic information will end up in that file, and we can check that out at the end of the wizard. So in our particular case, we are generating a airfoil that is defined by 5 sections. Each section is 128 points. It is a requirement that each section be of the same number of points and be of the same geometry input format. From this drop-down list, you can see that there are many input formats that we support, but for this one, we are going to use specifically X R theta by R. The number of blades for this particular row is 20, and the number of splitters for this particular case are none. It should be noted that the number of splitters is a ratio on the leading and trailing edge definitions, and most times most of our users find that the leading and trailing edges are well defined. However, the ADS tool suite does allow you to enhance the edges automatically for you. You can refer to the tech reference for the options. Now we are going to import the geometry data. So for the 5 sections that define our airfoil, we are going to bring in a file for each. Now each of the sections defines a particular span point on the airfoil, and it should be explicitly defined inside the geometry file. For our case, we are defining at 10%, 30%, 50%, 70%, and 90% spans. Once you've done that, you have the ability to adjust the airfoil as you need. We will not be scaling or rotating the airfoil as is. Now we are going to define tip clearances and hub clearances for our particular model. We are defining a tip clearance of 0.02 inches, and it is a constant clearance along the tip. Following that, you will want to initialize the flow field. What we have here are defaults for static, stationary air. The rotational speed is 0, meaning that it is stationary, and then the rest of the values are defaults for air. You have the ability to change it as needed if you are specifying something else. For aerodynamic conditions at the inlet, what we are going to define is 1 point at the 50% span. You have the ability to also import the values if they are already defined in a file. You can also define exit plane static pressures. Once you've done that, now we are going to get into the computational boundaries. The computational boundary is defined by 4 points at the upstream, 2 at the upstream, and 2 at the downstream. The H is at the hub, and the T is at the tip. Here we are defining our computational boundary. Next, we will want to define the end wall. This will complete the computational boundary that we have defined. Here we have the ability to import an end wall that is already predefined for us. As you can see, our end wall is defined by 2 points, with each point defined by 2 points. One at the inner diameter and one at the outer diameter. It is not necessary that the inner diameter x value and the outer diameter x value be equivalent. So congratulations, we have now completed the aero geometry data entry. We will go into mesh settings. The mesh generator wand has many settings that is possible. For example, we have the wand supports many mesh formats. But we highly recommend the OHH mesh for viscous flow analysis. We find that this gives you the best combination of accuracy and speed. But however, you can use other types if you so need to. Okay. For mesh fan out, we will use fan out on both edges. Okay. And for tip and hub clearances, because we do have tip clearance, we will define a tip clearance mesh. 8x8 is a recommended value for this. If you do not have a tip or hub clearance, this value is a don't care. For the mesh granularity, we also have many options for you. Some are already preset. However, if you feel you need to be more specific, you have the ability to add in your own values. However, what we recommend is fine. This is a combination of speed and accuracy that we find is very useful. Now Leo, the flow solver, also has some settings. You have some flow simulation models that you can use, and turbulent flow simulation is the one we recommend. Always use flow convergence acceleration. There really is no point to not use it. So if we go down, we see that there is the iterations to execute. This will determine the total time that the simulation takes. You also have the ability to determine when printout of performance data occurs. We've decided to print it out every 50 iterations. And also you can specify the iterations between plot file generation and restart file generation. Here we've defined it as 100 iterations. You also can plot out all the performance data into one of many plotting formats. We'll pick TechPlot for now. And you're finished.